In chapter 5, we are talking about polynomials. And polynomials are arguably one of the most important things in math. Like everything is a polynomial. And you'll see that at some point in your future, you're going to prove this really cool theorem that pretty much everything you've ever cared about or you've ever talked about in mathematics, I don't care how wild or crazy it is, it can be written in terms of polynomials. And so at first, without knowing that, without seeing behind the curtain, when you're just taking math and you're talking about polynomials all the time, it's like, why? Who cares? And then they try to give you a few examples of how polynomials could be used to do such and such. And it's always a contrived example. Like you're taking physics right now, right?
Yes.
And so you've probably seen parabolas to describe motion of something falling or whatever.
My physics class is a complete disaster, so no.
Okay, well, and the idea is like if you have an object, if I take this and throw it up and then catch it, we could use a parabola to describe that. A parabola is a polynomial. And the thing is, though, there's always this caveat, which is like, but it's not exact because we're not taking air resistance into account. There's friction and stuff like that we're not doing. And so it's like, yeah, it's a parabola, but not really. And so you think like, who cares about polynomials then if they're not really anything? And then you get a bunch of contrived examples, which you're going to see a lot of them in this class. Like it'll say that this polynomial can describe the revenue that a company gets over this amount of time. And then they give you some kind of question about it, but it always feels contrived. And so you're like, why do we worry about polynomials so much? Well, it turns out that everything's a polynomial. Like everything's a polynomial, and you could prove that. And it's cool stuff when you do, but you won't see that till calculus. And so why do we study polynomials? Well, because they're everywhere. And we want to, right now, at this point in our mathematical career, start to work with them. And we want to start to learn things about them so that when they show up later and we're actually using them for real world stuff, then we know what we're doing. Mm-hmm. So that's why we're going to spend almost the rest of our time in class talking about polynomials. And so here we go. Your book gives a bunch of definitions that I don't really care about. Like it says that, so for instance, let's just go ahead and write down a couple of one of these guys. It gives us, let's do this one, 5x minus, let's say, xy. And I guess I don't need to use the book's example. I can just make some stuff up. How about 2x squared y? Okay. It says that each one of these things are terms, right? And okay, cool. Now, we probably won't make a big point of that. What you are going to hear a lot, and something you have to know, is that the numbers in front of each of these variables are called coefficients. Mm-hmm. Right? And you've probably heard that 1,000 times. Another thing to know is that if you don't see a number right there, there's still a coefficient there. That coefficient happens to be 1. And by what we usually do actually is think about a polynomial as being strictly addition. So when you have minus xy, it's actually plus a -1 times xy. So when you see something like that, like if you have 2x squared minus x plus 2, and I say, what's the coefficient in front of the x term? You would tell me, well, it's -1, right? So that is going to be important that we know that. Okay, it talks about the degree of a polynomial. That's also kind of important, although the book, and there's like problems in the book which really, really try to drive the point home, and they make a big deal out of it. Not too worried about that. But the degree of the polynomial is the highest, I think about it as like the highest order or the highest power when, and this is where it gets weird, but when you add all the powers together in a term. But now, and so when I'm looking at this, basically, this guy has degree 1 because he is x raised to the first power. This is x raised to the first, y raised to the first. So altogether, the degree of that is 2 because 1 plus 1 is 2. This is 1. This guy, what's the degree of x squared y?
3.
3, exactly, right? And in practice, we're not going to worry too much about being able to identify the degree of some kind of mixed variable polynomial. That's not really important. What is going to be important, though, is when we have a polynomial of one variable, let's say something like this. Let's say 5x to the 5th plus 2x to the 3rd plus, how about x squared minus 45? We could say, I could say what it, then the degree of this polynomial will be the highest degree of the terms, or it'll, you see what I'm saying? What's the degree of this polynomial?
10.
No, now you see, now this is the thing. So it's the degree of the highest term, and I didn't say that. Like I just, yeah, it's, we look at the highest term. In this case, it's x to the 5th, and so we would just say the degree of this entire polynomial is 5. So the only time you're adding up the stuff is when you're talking about in a term. So we could say this term, like you just said, has degree 3. This term has degree 1. This term, since it's 1x and 1y, has degree 2. This guy has degree 1. And so then we, after identifying all those, we could say, well, the highest order is 3. And you see, I still call it order because, yeah, anyway, degree, the highest degree is 3. Therefore, we just say this entire thing then has degree 3. Does that make sense?
Uh-huh.
And it seems arbitrary, and it kind of is. It's just that, like I'm saying, in practice, we're going to need to look at a polynomial like this and be able to say, okay, what's the highest degree? And that, because that will be important when we identify to be able to identify the highest degree in a polynomial. And then we just say, it's kind of like by convention, we just say then that polynomial has that degree. It's whatever the highest order is. So still saying order. That could be really confusing. So, and in when you're doing different things in math, you might call it the order of a polynomial. So if you hear me say, what order is this? Or this is of order 5, I mean degree, and I'm sorry, and I'm working on it. But anyway, so, okay. So that's going to be important to know, just to be able to look at a polynomial, find the term with the highest degree, and then say, ah, yeah, that's degree whatever. But again, I'm not concerned if we're calling it'll be important in practice later. Right now, I'm not going to be like, what degree is this polynomial? It's going to come up later. So, okay, now they say a polynomial in X is any expression of this form. A to the n, x to the n plus a n minus 1, x n minus 1, and we go all the way down to a squared x, or it's not a squared, I'm sorry, you'll hear me say sub 2, and that just means I'm calling this thing, I'm giving that thing a subscript. So as I write something, I might say b sub 3. And that means b with a subscript 3. We'll get into that in just a second. Or I might just call it b3. And so anyway, so we're about to go into this and talk about what all this means here. Okay, so this in general is what a polynomial looks like. A polynomial of one variable. We usually write it in descending order. That is the degree of these guys. We take the highest degree, put them over here on the left, right? And it's understood that n could be any finite number. Maybe n is 25. And so I have the 25th, x to the 25th, plus a to the 24th, x to the 24th, and so on, all the way down to a2, x squared, a1, x, a0. You'll notice each of these coefficients, right? Instead of like up until this point, and especially when we were working on systems, we would write something like this. We would say like ax plus by plus cz equals d, or something like that, right? And this is fine as long as you know you're only going to be working with 3 variables, or if perhaps this was like an x squared, and this was like, I'm sorry, that's like an x, this is like an x squared, and this were, say, an x to the 3rd, then it would be fine as long as we know we're only going to be dealing with 3 things. We only need 3 letters. We're good to go. But in general, we don't know how many letters we're going to need, right? And so that's why we are using these A's here. Because frankly, if it's bigger than 26, I'm going to run out of letters. And I'm going to have to throw in an X in there, and that's going to look terrible. And so you can kind of see that this is nice. Another thing that's nice about it is you don't have to really worry about what number you're putting with something, because the thing that goes with the squared term is, a 2. The thing that goes to the, I didn't write the power up there, but X by itself is the same thing as X to the 1st power. And so it's nice that those ones correspond. Again, I didn't write it here, but x to the 0 is equal to 1. By the way, any number raised to the 0 is equal to 1. Negative 27 raised to the 0 is equal to 1. Believe it or not, 0 raised to the 0 is equal to 1. You could prove that if you take calculus. You could show that that's true. But so my point now is any number raised to the 0 is equal to 1. This will be helpful later on in our class if you just remember this from now on. Like any number raised to the 0 is equal to 1. Okay, moving on. So we didn't write it there because he's equal to 1, but this is nice because it's just like writing x to the 0 power. And go figure, the 0 matches with the 0, the 2 matches with the 2, the n-1 matches with the n-1. And that's just a fancy way of, like when I'm writing n-1, it's just like saying, yeah, the next one down. So if we knew that my highest degree of this was, say, 25, this is just a fancy way of saying, yeah, we're climbing down. So the next one is 24 and so on and so forth. Each of those are just numbers. Right, they're coefficients. And so, like A2, for instance, might be -1. And n-1 might be, I don't know, 5, right? This is just the same way that these represented any constant numbers back when we were working with, make this back into a linear equation. Back when we were working with this type of stuff. Same thing here. There's no difference. It's just nice to have a little subscript there so that we could write stuff like this without running out of letters. Does that make sense? Mm-hmm. Okay. So usually we write them in descending order, right? Polynomial functions. So given any polynomial, we could turn this guy into a function by just saying, okay, we could think about this as a function of x, where the output is what you get when you plug in some value for x. So I want to do a couple of examples there because this shows up on your homework tonight. So I'm going to do problem 2 from 5.1. It says q of x equals negative 5x to the third, negative 5x to the third, plus 7x squared, minus 12. Right. Real quick, what's the degree of this polynomial?
3.
Good job. Yes. 3, because you looked and you said, it's basically, it comes down to what's the biggest number you see right there. And it gets a little tricky if they're mixed, and we won't be dealing with those too much, right? Like if I had some kind of polynomial that was of 2 variables and you had like a 5x squared y to the third and so on and blah, 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 then you'd have to use your brain. But in this point, with most of the ones we're working with, it's 1 variable, and we can just say, yep, biggest number right there is 3. It's a degree 3. Okay. So the book will ask you to compute q of 3. So let's go ahead and do that. Q of 3. This is exactly what we've been doing this whole time, right? Like with functions, is that here's my rule for a function. It says if I plug in an x there, I do these things with it. And so if I plugged in a smiley face, I'd have a smiley face cubed, I'd have an x or smiley face squared, and so on. So when I plug in a 3, I just substitute it in. What I like to do personally is, as I'm about to write this down, everywhere that I see an x, I put a parentheses. This helps keep me honest. And right now, when you're plugging in a positive 3, it's not that really, excuse me, it's not that necessary. But when you plug in a negative number, you'll see in just a second, it will make this a lot better. So I'm going to evaluate q of 3. I just copy this exactly, but parentheses instead of the x's, and then I just plug in the number. What's nice about having this written right here is I can check myself real easy and say, yeah, everywhere that I saw an x to begin with, do I now see a 3? Yep, good to go. So now I'm going to go ahead and evaluate. And remember this? Have you ever seen that acronym before?
Yes.
Yeah, right. So there's an order of operations. And when we're doing polynomials, right? Well, look at what I used. Oh, nice. Okay. So we're gonna, like, that's pretty much already done, right? So of course, exponents come next. So I'm gonna evaluate the exponents next. So what is 3 to the third?
9.
3 to the third.
Oh, no. 27.
27, yeah, 9 times 3 is 27. So 27. So what I'm going to do here is negative 5 times 27, okay? Plus now, what is 3 squared?
That is 9.
That one's 9, yes. So 3 times 9. I like to use parentheses still, right? Like, I'm going to keep my parentheses as long as I can. Now we have negative 5 times 27. I have no clue. I'm just going to do this right here. 5 times 27. 7 times 5, I guess, is 35. 2 times 5 is 10. Plus 3 is 135. So altogether, we should have a minus 135. Yeah. 7 times 9 is what?
63.
Yeah, I gotta use my fingers. Do you know how to do that with your fingers?
No.
Yeah, check this out. This is great. So 9 times 2, you go 1, 2, and you have a 1 and an 8. It's 18. 9 times 3, you go 1, 2, 3. You have a 2 and a 7, so it's 27. 9 times 7 would be 1, 2, 3, 4, 5, 6, 7. You put that finger down, you have 63. I swear, every time I multiply by 9s, I do that. I go 63. So,
That's so cool.
isn't it? Pretty cool. Homework tonight, prove that that's true. No, I'm kidding. Okay, so 7 times 9 we said was 63 minus 12, and I'm not going to work that out. I have a feeling that if you were so inclined, you could work that out right there.
It's negative 84.
Oh, nice. I believe you. I'm just going to go and write it down. Negative 84. So we could say then Q of 3 is equal to negative 84. This will be nice in the future, like if we're graphing and stuff like that, we would know that when I plug in a 3, I get out a negative 84 because, again, this thing is a function, right? It's a relationship between X inputs and Y, or in this case, we could call it Q outputs. And it says that when I plug in a 3, I get out a negative 84. That's what it means, that Q of 3 is equal to negative 84. Okay. Let's move on. The next type of problem like that, it's actually the same problem. It's still problem 2. It says to evaluate Q of negative 1. This is where parentheses are your best friend. I'm going to say, okay, I have this written the way I like it. One's right under the other, so I don't have to use my brain. I'm plugging in something for X. So everywhere I see an X, I'm going to start by just using parentheses. Okay, now everywhere that there's parentheses, I got to make this match up with that. Instead of plugging in an X, I'm now plugging in a negative 1. And so we end up with that. Okay, there's nothing inside the parentheses to do, so I'm moving to exponents. What is negative 1 to the 3rd power? Don't think too hard.
Negative 1.
It's negative 1, right? But if you're like, if you hit that wall where you go, wait a minute, whoa, come back to something that you know. And for instance, this is what goes through my brain. Something to the 3rd power means multiply it by itself 3 times. Okay, so if I have negative 1 to the 3rd power, that means I take negative 1 times negative 1 times negative 1. Now I could kind of see what's happening here. A negative times a negative is a positive. Okay, so I basically just evaluated those two right there. I said negative 1 times negative 1 is positive 1. Mm-hmm. Negative 1 is still hanging out there. And so negative 1 times 1 is negative 1. Now notice, and this is something that we might as well go ahead and talk about this now because it's going to come up so many times in the future, that when you have a negative 1 and you multiply it, and you raise it to any even power, let's say I raise it to the 6th power, what do I get?
You get a negative?
Let's think about it. So 6 is an even number. 1, 2, 3, 4, 5, 6. And this is the idea. Even powers, right? You always have you can always group 2 of them together, right? So these 2 come together to give you a positive 1. These 2 come together to give you a positive 1. These 2 come together to give you a positive 1. And so the answer is going to be positive. So then by that reasoning, I could say, well, if I made that a 7, it would be the same thing as doing the 6 of them, but then I'm just adding on an additional -1. And since I know that the 6, it's even, so we have those two pair off, those two pair off, those two pair off, and the entire bit becomes 1, then I have that odd man out. Funny how that works out. Like that's like English language, right? Like, oh, the odd man out. Well, there's an odd man out, right? That when you have an odd power, there's everybody pairs off except for that 1 right there, buddy. And so that will come out to be a -1. That's going to be true for any odd power. And we can kind of see that, right? Any even power, let's say 102, right? I don't need to draw it out anymore. I could just do this. Well, -1 to the 102, I could just say, well, it's an even power. And so there will be, and I could work this out and say, well, 51 and 51 of them would pair off together. And so every negative cancels out. And so I could say, it's a positive number. I mean, yeah, it's +1. Similarly, I could say, well, any odd number, how about 7,401? I could say, well, 7,400 is an even number, so those all pair off and they all kill each other, right? The negative and the negative combine to make a positive, and I do that 7,400 times, but I would have that one odd man out that would make the entire thing negative. So basically, the takeaway point here is any negative number, well, yeah, actually, let's do it that way. Any negative number, -a, raised to an even power is a positive number. Any negative number, say -a, raised to an odd power will be a negative number. Harder to compute if it's not 1, right? When it's -1, you're like, oh, well, it's either going to be 1 or -1. Now, if it's -2, then you might have to use your brain, but you don't have to use your brain for this part, right? It's like, well, in the end, so for instance, if instead of a -1, I were plugging in a -2 and I raise that to the 3rd, my first thought is, well, it's a negative number raised to an odd power. The answer's got to be negative. And then I think, well, what's it going to be? Well, 2 times 2 times 2 would be 2 times 2 is 4 times 2 is 8. And that's kind of what goes through my brain. And really, let's just kind of verify that. That says the same thing as take -2 times -2 times -2. And now we can kind of see, yeah, the evens are going to pair off here, right? And that gives me a +4. And then I multiply by -2. +4 times -2 is a -8. Check. So there we go. Okay. So -1 raised to an odd power is what?
-1.
-1. Now, -1 raised to an even power is
1.
+1. -12. There we go. So now I have a negative times a negative. And like I said, this is why parentheses are your best friend. Like, I've had so many students over the years who are like, for some reason, just they don't want to write parentheses. They're like, no, I'd like to just do it in my head. Like, okay, get the wrong answer, have fun. You know, like they're your friend. They're there to help. And now I could, like, seeing it this way takes a lot of the guesswork out of it. I have a -5 times a -1 is what?
5.
+5. 7 times 1 is a 7. -12. And I end up with, I think that's 0. 5 plus 7 should be 12, -12 is 0. And so I could say then Q of -1 is equal to 0. So those are the first two questions. The first two questions of your homework are like that. Okay. Moving on, collecting like terms. So we're going to do number 12. Am I good to erase all this stuff?
Yes.
All right. So this is something I wanted to talk about briefly, if it's possible for me to talk briefly. So we have 5x squared y. Okay. 5x squared y squared plus 4x. Ooh, that's x cubed minus 8x squared y squared. And minus 12x to the third. Now, collecting like terms, right? What they mean by like terms, we know each one of these is a term in a polynomial, and we want to collect like terms. It's basically saying like you have 5 apples, right? This is a type of thing, and you're going to take away 8 apples. How many apples do you have left? That's all we're doing. We're combining terms that have the same variables, right? And we could see that this guy minus that guy all together should give me a -3, right? X squared y squared. And what about these guys? Can I combine them?
Yes.
Yeah, because they're the same thing, right? This is an orange. You have 4 oranges and you're taking away 12 oranges. How many of them should I have left? Yeah. What do I get when I put those together?
-8 x squared cubed.
Yep. There you go. And that's pretty much all that there is to this. It says combine like terms. You're just finding terms that are alike and you're combining them. Now, I do want to talk about this briefly because this seems, I don't know, at least when I first heard this, I'm like, and I've had students who have brought this kind of thing up. In some sense, you're like, let's just say 5x squared. You might want to say, well, why can't I combine those? I mean, they're both x's, right? And to some extent you can, but you might want to say, well, I don't know, it looks like I should have 7 of something, right? 7 of something, because I have 2 of something and 5 of something. I should have 7 of something. And that would be true if these were always going to be the same thing. And as a matter of fact, they're absolutely true when x is equal to 1, right? Because if I plugged in a 1 here, then they would be the same kind of thing. It's like, well, yeah, that's an apple and that's an apple. They're the same type of thing. And we can kind of see that, right? Like, well, that's just 2 and 1 and 5 and 1. Those are the same type of thing. We have the same thing going into each one of those. So it has to be the case that that's 7 of whatever that thing is, which is 1. But that's only going to work at one point, at one value, right? There's only one value of x in the world that's going to make that thing true. And the whole idea behind polynomials is that these are all variables. We're going to let them vary. We are going to change them. They're never going to be the same thing always and forever. We're going to plug in a 5. We're going to plug in an 8. We're going to plug in a 2. And when we do that, let's see what happens. When I plug in a 2 for x, now I have 2, what is this? 2 cubed is equal to what?
8.
8. And 2 squared is equal to what?
4.
4. And so now we can see you can't just combine those. That's an apple and that's an orange. We don't have 7 of anything, right? These are different things. And so That's why we got to keep these terms separate. You can't combine them if they don't have the same variable raised to the same power. But when they do have the same variables raised to the same powers, then they are exactly the same. I don't care what you plug in there, right? Like in this case, this guy and that guy, I don't care what value of X you use, that value of X, like when I plug it in, let's say square, or when I plug in a 2 cubed is equal to 2 cubed, and now you have apples and apples, and then you can combine them. So I just had to go into that. So makes sense why we have to keep terms separate and which ones we can and cannot combine.
Yes.
Okay, cool. So moving on, find a polynomial function at a given value. Okay, so I'm just going to do something very much like this. I'm giving you some problems that give you a polynomial. So polynomial of one variable, and we're going to call it cube of x equals, let's say, x cubed minus 2x squared plus, how about 3x minus 4. And the problem's going to say something like this. Find q of negative b. And so right now, if I gave you a number like we did before, you would just plug the number in and all of that would work out to be numbers. You'd have to do some thinking. You'd have, like if I gave you the number 2, you'd have to say, okay, 2 cubed is 8. And then that squared is 4, so minus this. And you'd be able to actually calculate a number in the end. In this case, you're not going to end up with a number because I told you to plug in a negative b. And so when we do that, what we're looking for here is that you just like we did before, I'm going to say, well, I'm plugging in a number into a function. Everywhere that I see an x is now going to be replaced with that. So everywhere that I see an x, you'll notice I do the exact same thing I did last time. I'm going to use parentheses to kind of prep myself for what I'm about to plug in there. Now I'm going to plug in that number. It happens to be negative b. Okay, negative b, negative b, negative b. Now here you could stop and you'd be absolutely correct that q of negative b is equal to that quantity, but we don't want to do that. But in this case, for these examples, I do want you to calculate what this is. So what is negative b cubed?
Negative b.
Negative b raised to the 3rd power, right? Because let's just think about this. If I said, what's negative 2 cubed? You'd say, well, negative 2, negative 2, negative 2. And you'd know, okay, yeah, the negatives are going to come out, right? And that's going to be then a positive 2 squared times negative 2. And then you have, okay, 2 squared times 2 is the same as 2 cubed, but it's a negative. So you're going to end up with a negative 2 cubed like that. And yeah, before we actually calculated it, we said that's equal to 4. And then when you do it again, you multiply it by 2 again and you get 8. But the only thing we really need to remember here is, well, so the reason we can't do that in this case is we don't know what b is, right? And so this works out in the same way. I just look at it and go, it's a negative number raised to an odd power. It needs to be negative. And so I get a negative what? Well, whatever number that is, I could pretend it's a positive number. When I cube it, I'll get, well, b cubed. And so if it were negative 2, right, if b were 2, we'd have negative 2 cubed, and we'd do this type of thing. And it would be true that you would get a negative 2 cubed. So there you go. Does that make sense?
Yes.
And so that's what we're looking for here with this type of thing. So we want to try to simplify as much as possible. And then in the end, we're going to say, okay, is it positive or negative? Okay. Now, What about negative b squared? What is negative b squared?
Would that just be b squared?
It'll just be b squared. There you go, right? So look at what I've done. I've just copied this down without using my brain. And I just did what you said. You said negative b squared is negative b times negative b. Negative times negative is a positive. And so now we have a positive b squared, just like that. Okay, what's 3 times negative b?
Negative 3b.
Negative 3b. And so I'm looking out here and saying I need to flip that sign. And so that's how we would write that, just like that, negative 3b. Finally, minus 4 didn't change, and so we have minus 4. There we go. You'll notice, yeah, like, so this is what we're looking for here, is that when we plug in a negative here, we just evaluate. For odd ones, that entire term becomes negative. For even ones, that term stays the same sign. For odd ones, right, x to the 1 is x to an odd number, then that term changes sign. And that's what you should see there. And yeah, and finally we bring everything out. Like I don't leave it written like this. I bring that negative all the way out. So, okay, that's what we would do in that case. Now here's a tricky one because there's one very much like it. Sorry, I just erased that. I hope you were done.
I'm good.
Okay. Another one that they're going to do is something like this. They're going to say, evaluate this at c over 2. So again, not going to use my brain. I'm just going to say, okay, something cubed minus 2 times something squared plus 3 times something minus 4. What's that something? Well, it's c over 2. Okay, so c over 2, c over 2, c over 2. Now I'm going to have to start using my brain. C over 2 cubed, let's just think about that. A couple ways we could think about it. If you like, if you've memorized a rule, you could say that's the same thing as c cubed over 2 cubed, which should be c cubed over 8. But when I look at that, what goes through my brain is, wait a second, something cubed means multiply it by itself 3 times. Okay, so that's c over 2 times c over 2 times c over 2, which means I have on the top altogether, I have c times c times c, which is c cubed. On the bottom, I have 2 times 2 times 2, which is 2 cubed, which I could write if I were so inclined as c cubed over 8. So that's kind of what goes through my mind when I see this. I'm like, wait, some fraction cubed means that fraction multiplied by itself that many times. And so whatever number that is going to be how many of them I have on the top. Whatever number that power is going to be how many of them I have on the bottom. And so I just kind of go straight to here. And since I chose to do it over 2, it's an easy one. It's not like over 17. I could just go, oh yeah, 2 cubed is 8. And so I would just go ahead and write this guy as c cubed over 8, like that. What about the next one? What is c over 2 squared?
C squared over 2 squared.
Yes, c squared over 2 squared. There we go. So which would be over 4. So so now watch what I'm gonna do. I'm gonna do this one step at a time. I'm gonna go, that's c squared over 4. And then I'm gonna come back to it. Okay, so plus. Plus, and we could write this a few different ways. I could go ahead and just do that as 3 times c over 2, whatever. Well, the thing is, if I want to think about this as a polynomial, well, one more nice little cancellation I could do here. And that's, I notice we have a 2 and a 4. What happens there? How would I rewrite that?
You can divide both by 2. So you have 1 over, or no, -1, and then c squared over 2.
And so the way I think about it is, I know it's negative. There's nothing crazy going on there. So whatever that sign is has to just come down. And then I see the 2 cancels, and so I'd be left with a c squared over 2. Okay. This thing is 3c over 2, but this kind of suggests something is like I could write this as 3/2 times c minus. Now, remember that problem we had with the slope last time? It was like, what is the, if that's my thing, what's the perpendicular slope to that? And we kind of thought about, and what we said is what, oh, and it was actually a negative. I said, well, what you got to do is take this step where you pull that guy out and think about him like that. We could do the same thing here. Like if you were to just answer this, that would be fine. But it's nice to be able to think about this in terms of a polynomial. Remember how we thought of a polynomial? It was some constant times something like this, some other constant times x squared, some other constant times x, and then finally some other constant. So again, you don't have to do what I'm about to do, but if I were to ask you what's the coefficient of the c squared term, you look at it this way, it doesn't make much sense. But if you had it like this, if you'd written it like that, you'd say, well, the coefficient is whatever number that is right there. And so we could rewrite this by saying, well, this is the same thing as 1/8 times c cubed. This is the same thing as minus 1/2 times c squared. This is, I went ahead and wrote it that way, 3/2 times c minus 4. And so then if I were to ask you, what is the coefficient in the c squared term, you would tell me what?
-1/2.
-1/2. There you go, right? Because we imagine that it's always plus, and when there's a minus, it just means that you're plussing a negative number. And so we would say -1/2 is the coefficient for the c squared term. Yep. Okay. So that's the kind of stuff you're going to see for 15 through 18. Now, there are a bunch of word problems that we're not going to do because,
okay.
I mean, well, really, it's just this. It's like they give you a polynomial and they're like, evaluate this, and they tell you like this represents this. Now evaluate it where a equals 5 and b equals 7. Okay, this is all you're doing right here. You're just plugging values in. So I don't care. So, however, oh man, I'm giving you 2 challenge problems from this section. And oh boy, do I love problems like this. So one of them, they give you a box and it's an open box. And so I want to go over this because the drawing is a little ugly. And so I'm going to try to explain what's going on here. They have a drawing that looks like this. And they tell you to find the area of the box. And you're like, it's a box. It doesn't have an area. Like it has a volume, but so what they mean is the surface area here. So if we took this box and it's an open-ended box, there's no cover to this box. It's just it's a box. So it has a bottom part and it has these 4 flaps, right? So what it's asking you to compute is the area of all of the flaps and the bottom of it. And so we'll just go ahead over it. We'll say, so, and they give you dimensions. They say it's x by x. So the base is x by x and the height is h. And they want the surface area. So what we're going to do for that, this is problem 35 from your homework. What we're going to do, the way I like to do it, is just imagine, okay, well, I just have, if I broke this guy into 4 little rectangles, we would have the piece from the back, we would have the piece from the side, we would have this piece from the side, we'd have this piece from the front. We would also have the bottom of the box. The bottom of the box, it tells me, is x by x. And so the, I guess, width and depth is x by x. So what's the area of that thing right there?
X squared.
X squared, right? Now, each one of these, you'll notice the length on one of them is x, right? The length here is x. The length in the back is x. The length right there is x. And in every case, the height is h. And so you have by h. What's the area of one of these guys?
X times h.
X times h would be the area of that guy, or hx, it doesn't matter. And so how many of them do you have altogether?
4.
4 of them. And so we know the area of one of them. We know the area of that guy. So really all we need to do is add up that many plus the area of that guy, and we have our answer. Make sense?
Uh-huh.
Okay. Okay, moving on. 36 is tough, and it's a challenge problem, and there's no answer in the back of the book. And so, yeah, 36 is similar to it. They give you a sheet of paper or whatever, cardboard or something like that, and it's 12 by 12. Then they say that you measure a square inside of it, that its width right here is x, its width right here is x. And then what you do is cut out little squares right there. And then, and this, I want to go over this because it's weird, but you're then, after cutting out those squares, you're going to fold that up to make a box. Does that make sense? Can you imagine that if you took a piece of cardboard that was 12 by 12, you cut out these little squares right here, and then you took each one of them and folded them up? Well, you would end up, it's very similar to what you'd have in the last case. You have a box whose base is x by x. Then when you fold that flap up, you would have your side flap right here. Fold that flap up, and you're going to have your flap right there. Fold that flap up. Got that guy. Fold that flap up, and you got this guy. And they ask you to find the volume of this box. So, how do we find the volume of a rectangular prism? And let's say it has, the width is W, the length is L, and the height is H. What is the volume of that thing?
I forget.
It's just length times width times height.
Okay.
So it's, you take each of the dimensions, you take the this way times this way times this way, and that's how we define volume. So to find the volume of this box, I know that the width is x. So I'm going to say, okay, then the volume is x. The volume is the width, which is that part, times the length, which is that part. So x times x times whatever this height happens to be. And your mission, should you choose to accept it, is to find what that value of h is. And if you look here, you could see, like, yeah, that's h right there. That distance from there to there is h. And I didn't draw this well, it's squares, but that distance is h from there to there. That distance is h from there to there. Ditto from here to here, right? They're all squares. So that height that you have is whatever distance that is. This is a challenge problem. It's going to be difficult, but you got to find that out. So there's that. How much time do we have? We are already over. Does that make sense what you need to do?
Yeah.
Yep. Little hint is if you know that that entire distance is 12, and you also know that that length from there to there is h, and you know that that length from there to there is h. There's one more bit of information you could use to try to put that all together. But yeah, that's a fun one. That's yeah. So, okay. Let's see. So I will give you your homework in just a second. Addition and subtraction of polynomials. You said you read that, right?
I did.
Subtraction of polynomials. Did it make sense?
Uh-huh.
It seems so straightforward that I wasn't planning on really talking about it today. I mean, like the same way that you collect like terms, that's all you're doing when you add or subtract a polynomial, right? Like, I'm going to go ahead and erase this if we're good to go.
Yeah.
All right. Like, we've already added and subtract, we've already collected like terms. So when we did something like this, 2x to the 5th plus 3x squared minus 3x, no, let's go minus 2x squared plus x to the 5th. We basically said, yeah, okay, collecting like terms, wherever I see that and that, I could add them together and we get 3x to the 5ths. We have 3x squareds minus 2x squareds. That leaves me with 1x squared. Well, yeah, that's the same thing as just adding this polynomial to this polynomial right here. It's really the same thing. What we could do to help, help organize this is to, if you're told, add this one to this one. What I like to do is write them in descending order. So I'm going to say, okay, 2x to the 5th plus 3x squared, and I'm going to add that to, and then I write this one in the correct order and just say, well, okay, x to the 5th right here plus 2x squared. And when it's something easy like this, we just collect like terms and whatever. But as they get more complicated, it's nice to be able to organize it like this. That way I could say, oh, I have 2 of those and 1 of those. It makes 3 of those. 3 of those and 2 of those. That should have been a minus, but whatever, you get the idea. 3 of those and 2 of those make 5 of those right there. Okay, now if I said subtract, that from that, I just had to do it that way. I would say, okay, subtract that from that. I have 2x squared plus an x to the 5th. So I'm going to write it in the descending order. So I have that. And I subtract off a polynomial. I love to use parentheses here. So I'm subtracting this right here. And what I like to do is go ahead and I distribute that negative in. And I think, okay, that's the same thing as subtracting each of the terms, x to the 5th minus 3x squared. And then I would have, I guess, minus 1 x to the 5th minus 1 x squared, something like that. Same thing if we wanted to do something like this. Sorry, I didn't bother to ask if you were done with that. If we had 3x cubed plus x minus 2 minus some polynomial like this, like, how about x cubed minus x squared plus 2x minus 1. What I like to do in this case is think, well, it's the same thing as if I subtracted off, or if I distributed this negative. That's going to flip the sign in each one of these cases. And so I could say, okay, 3x squared plus x minus 2. That's the same thing as minus an x cubed. And then a minus minus is a plus x squared. A minus plus is a minus 2x, and a minus minus is a plus 1. And so now, that should have been a cubed right here, sorry. Now, again, I'm just collecting like terms. I could put them one under the other. If it's written like this, I usually just roll with it like that and think, okay, I have 3x cubes minus an x cubed gives me 2x cubes left over. As I do this, I like to mark off what I've done, especially in the future. These are going to get really long and unwieldy. And so I like to go, okay, what's my highest order term? The x cubes. Okay, so I'll knock those out first. And then I mark through them and go, okay, they're done. I don't need to worry about them. Now I'm going to look through and say, what's my next highest order term? Oh, it looks like an x squared plus x squared. So I'm going to go plus x squared. Mark through it. I know it's done. Now I go through and say, okay, now the next thing would be x's. And so x's, I have a positive x minus 2 x's. I guess 1 minus 2 should give me minus 1 of them. So minus 1x. Mark through them. They're done. Now negative 2 plus a 1 gives me minus 1. And so now I'm done right there. And I could see, yeah, that's what we just did. Did you follow that? Does that make sense?
Mm-hmm.
Okay,
I'm tracking.
cool. So that it's really straightforward. You're going to get a bunch of practice with that. Actually, not too much though. So, okay, I think we're ready. I'll give you the homework assignment for this evening. Okay, so I'm going to erase this. Are we good?
Yeah, we're good.
All right. Homework. So, 5-1. This is page 208. So 5-1. This is page 208 through 209. Numbers 1, 3, 9, 11. 13. Then we're going to do all of 15, 16, 17, and 18. So 15, 16, 17, and 18. There's that. Then 35 and 36. Those are those challenge problems I told you about. 35, you pretty much already figured out. 36 is that one where you have to find h. And you're going to find h in terms of x. That's the idea, right? Like, you know that you have 12 inches. You know you've taken x inches out of the middle of it. And so then there's these two little bits left over. That bit is its length is h. We just need to write that in terms of x. It's pretty challenging, but it's, again, it's a challenge problem. So it's like, if you're having a hard time with it, don't worry about it. It's just trying to bend your brain a little bit. Now, section 5.2. This is page 212 to 213. Numbers 1, 5, 9, 13. 1, 5, 9, 13. 1, 5, 9. Wait, 1, 5, 9, 13. 15, 19, 23.
Yeah, oh, that one too. So 27, 39, 27, 29, 31. So 27, 29, 31. And then the challenge problem is number 33.